Okay, so here we are, higher level kinetics, topic 16, and this is section 16.1, which is all about rate expressions and reaction mechanisms. Reaction mechanisms are the steps by which a reaction actually occurs. It's very unusual for things just to collide, crash, bang, wallop, and the reaction takes place. It's actually a little more complex than that. The rate expression, as you can read here, links the rate of reaction to the initial concentration of the reactants. You may have thought, well, if I double the initial concentration by reactants, then I'll double the rate. But that is not always the case. There's only one way in which you can find out the rate expression, and that's by using experiments or from experimental data. Obviously, you don't have to necessarily do the experiment yourself. Okay, unlike Kc, and this is where a lot of people get themselves confused, you cannot just look at the chemical equation to find the rate expression. So, I've been very creative here, as usual. I've got a random reaction which I've called A plus B going to C plus D, and let's see what the rate expression, or rate equation as it's sometimes called, will look like for this. Well, the rate R equals the rate constant, more about that later, the initial concentration of A raised to some random power x, we'll find out what that is in a minute, and the initial concentration of B, again raised to some random power y. This x and y do not come from the chemical equation. They are not the numbers in front of A and B. So the rate is a measure of concentration against time, as we saw at standard level. Very often the units will be moles per decimeter cubed per second. K is the rate constant, more later, and we are familiar already with the square brackets being used to denote concentration in moles per decimeter cubed. Now x and y are called the orders of the reaction, or orders with respect to A or order with respect to B, and these are what can only be found from experiment. And for us, they'll always have a value of 0, 1 or 2. So if in your calculations you get an answer different to that, then sorry, you have gone wrong somewhere. Now, there are substances that don't appear in chemical equations but can appear in rate equations. So what are substances called that influence the rate of a reaction but do not appear in the chemical equation? Well, of course, they are called catalysts. So you might see an extra substance in the rate equation up here that does not appear in the chemical equation. So now these orders, let's find out a bit more about those. There's first of all what's called an individual order, and that is the x and y in the equation you saw before. There's also the overall order, and that is x plus y. In some of the calculations you'll look at, particularly on exam papers and in the worksheets, you'll have to work out an individual order of a substance, having worked out the overall order, but more about that later. So in the rate equation that's shown there, the order with respect to A is 1. Okay, no number there means power 1. So that's called a first order with respect to A. And it then doesn't take a genius to work out that it's second order with respect to B. Now, some thinking out loud here. If A is, let's say in our first experiment, 2, and we do another experiment and we use its concentration as 4, I've doubled A, The fact that there's no power here means that A is directly proportional to the rate. So if I double A in this instance, the rate will double. But have a think here. If I go from 2 to 4 with the concentration, the rate is proportional to B squared. So if I double the concentration, the rate will be quadrupled, 2 squared. But more on that in a bit. And here's the tricky bit. The overall order is third order. Okay, 1 plus 2 equals 3. I hope you didn't need your calculators to do that. Now you can have an order of 0. That means the rate is unaffected by how much of a substance is present. And we'll find out circumstances where that occurs and how that's linked into the reaction mechanism. So as I mentioned, order 1 means the rate is proportional to concentration. So if we double the concentration, we double the rate. And order 2 means that rate is proportional to concentration squared. So if we double the concentration of that particular substance, then we quadruple the rate, because 2 squared is 4. So let's have a look. To determine these orders, and we're only going to look at one technique for now, because that will keep you busy for plenty of time. So you do a series of experiments, you make sure they're a fair test, but you change the concentration of one reactant only. Then you change the concentration of another reactant, keeping everything the same. And from that, you should be able to calculate or deduce the rate expression, and then you can use that rate expression to calculate the rate constant and its units. That's a typical sort of IB question. So here we go. We've got a very creatively named experiment here with A and B, and what we have to do for this is exactly the sort of thing you might have to do for IB. Calculate the individual orders for A and B, the rate equation, the value of the rate constant, and the units of the rate constant. Again, that's exactly what we're going to do. And I think the slides I probably give too much information on, and I hope that doesn't confuse you, but let's have a look at how we solve this. So here we have the results table, just copied and pasted from the previous slide. But I've highlighted the 2 experiments you need to use to find the order with respect to A. Notice A changes and B doesn't, so any change in rate is down to a change in the concentration of A. And the same for B. Okay, A doesn't change between those 2 experiments, but B does. So comparing experiments 1 and 2, B is the same, A is 3 times bigger. Concentration of A goes up 3 times. What happens to the rate? Well, the rate is 3 times bigger as well. So that tells you that the rate is proportional to the concentration of A, and that means that it's first order with respect to A. Then looking at B, again, looking at experiments 1 and 3, A is the same, so any change is due to B. B doubles and the rate goes up 4 times. So that means the rate is proportional to B squared, the concentration of B squared. 2 squared is 4. So in this instance, it's second order with respect to B. So by combining those 2, that gives you the rate equation. The rate R equals K, don't forget that, A first order, B second order. Simples. Now, if we want to go on to the next step to find the rate constant, we have to do a bit of rearranging. And that rearranging is not rocket science. It just is the rate divided by the concentrations of the substances raised to the relevant powers. It's always K equals rate divided by all the rest here. It's never anything different. So to calculate k, we can pick any experiment we want. You could pick experiment 1, you could pick experiment 2, but I've chosen experiment 3. If you want to check, then just do one of the other experiments as well. And you get 8 times 0.5 over 2 squared. Have a check back at the tables just to see where you can see where those figures come from. And it doesn't take a genius to get that comes to 4. Now, but how on earth have I got these? I hear you say, well, you get the units for k in exactly the same way as we worked out the units for kc. So the units on the top here are moles per decimeter cubed per second. But on the bottom, we've got moles per decimeter cubed and moles per decimeter cubed squared. And all you need to do is the same cancelling down like you did for kc, and you should be able to convince yourself that that is the answer. That is moles per decimeter squared on the bottom here. Then when you bring it up to the top, you change it to dm6 moles to the minus 2. Okay, again, here's a second question. The maths on these are quite simple and straightforward, and you have to do exactly the same sort of thing as before. So calculate the orders, rate equation, the value for the rate constant, and the units of the rate constant. So think about which experiments are you going to use to find the rate with respect to A. Remember, you need A to change but B to be constant. And likewise for B, you need B to change but A to remain constant. So have a think about that, see how you get on. Pause the video for a minute and see if you can manage to work through that example. Okay, you can see what we'll be looking at next, graphical methods. But before we move on to that, there will be a virtual experiment. Well, it's some experiment results for you to use to deduce some rates. What I also want you to do is go onto my website, please, and there you will find a link to useful websites. Go on to Hot Potatoes, HL, higher level, and there are 2 exercises I want you to have a look at. Rate constant and units, and rate equations. Could you please have a look at both of those and have a go at them? And I will be setting you a worksheet to do on these rate expressions very soon. So please make sure you're up to speed with that so the worksheet makes sense. If you're struggling with the examples, then please pop me an email. Okay, see you soon. Bye.